Hey everybody, it's Norm from Tested.
And it's Jeremy from Tested.
Welcome to Projections, our show about virtual reality, and this week, more specifically, about augmented reality. So we've seen quite a few new augmented reality technologies now. We saw the Meta 2, I've used HoloLens, and this week we got to use something from the company Avegant.
These are the guys that made the Glyph, which was not an AR device or
a
VR.
VR device.
It was more like a portable television, which strapped on your head, kind of like Geordie LaForge, and it would beam images directly onto your retinas.
And they have pivoted from the Glyph. So their technology was what they call retinal imaging, which was basically two DLP projectors made by Texas Instruments, 720p projectors that were balanced around mirrors and went right into your eyes. No screen you're looking at, so really high fill factor, really bright display. But they've adapted that projection system into an augmented reality headset. Now, it's really tough to explain and show what that means, so maybe the best thing for us to do is to show you our demo and our conversation with Avegant's CTO about their technology.
At Avegant, we've really focused on bringing new display technologies to the market. So in the past, you might have seen a product we shipped called the Glyph. And that was primarily around bringing new display technology, what we call a retinal imaging display, to the market. Basically, instead of using a physical screen, we used millions of micromirrors to actually project light directly to your retina. There's some really incredible advantages to that type of technology that you might have seen in our product, like super bright, high-resolution images, very vivid, and really incredible performance, like really high frame rates and low latency. And that's what we did in the past, is taking these brand new display technologies to the market. So now what we're doing is really focused on new mixed reality technologies. We've taken the core retinal imaging technology we had in the Glyph, and now we're transforming that into these transparent mixed reality prototypes. And the new thing that we're really bringing to the table here is a new Lightfield display. The ability to bring Lightfield technologies to mixed reality is really an enabling experience for the industry, and really excited to show you what that experience is like.
So with the Glyph, with your last product, the image was projected straight into my eyes by a thing that was in front that was obscuring the world. So there was no way to do mixed reality with that. So now you're taking the same kind of projectors, but you're projecting them through a lens that allows me to see the real world?
That's exactly right. Okay. So we're actually projecting the image off of what's called a combiner. And what that allows us to do is to combine the light from the real world, from the outside, with the light that we're projecting into your eye. So now we're actually mixing these two, the virtual images with the real world now. And that's what's going to allow us to actually mix in virtual images into the real world experience. And by adding Lightfield to that, it's going to add a whole new level of realism and enable a lot of new experiences that you couldn't have before.
It sounds like there are two things going on. Like what you guys were just talking about is you could have turned the retinal display technology, these two DLP projectors essentially, and made it transparent by using like a partially silvered mirror, right? This is what the combiner is. But Lightfield is a whole separate thing. So explain what Lightfield display technology is, or what the experience is supposed to be.
Sure. There's a little bit of background about how we got to this point, right? What's kind of interesting is, we always knew that these kind of transparent mixed reality displays really is going to play an important part in the future of where these type of headsets are going, right? Toward potentially replacing your smartphones and computers down the road. What we found was that you could make a transparent display look pretty good, and with our retinal imaging technology, actually really high quality. But what we found was that without Lightfield, it's actually very difficult to make a really compelling experience. And part of that comes down to how we naturally see the world. When we think about how we perceive depth, how our eyes are actually seeing how far away objects are, there are a lot of different depth cues that we have, but when you start looking at things up close, like within a couple of meters, what really becomes important is this concept of convergence and accommodation, right? Basically the angle of my eyes, which is the convergence, and the focus of my eyes, which is the accommodation. When we grow up as kids, when we're developing our binocular vision, these two things are really tightly coupled together. If I look at my finger, you can see that my eyes are converged at this point, and each one of my eyes are also focused at this distance. These two properties need to be really in lockstep, right? And the issue we see in 3D displays today these non-light field displays, both in VR and in AR, is that they break these apart. And this is a pretty well-known problem. They call it divergence accommodation conflict, right? And the issue with having this conflict is there's some physiological problems. You know, a lot of people get eye strain, headaches. It's just like you ever go to the 3D movie and put on those 3D glasses? A lot of people don't feel good when they do that, and like they feel a lot of eye strain and stuff. But the other problem that's actually a bigger problem, I would say as big of a problem in mixed reality, is when you're looking at transparent displays. If I want to put a virtual image into your real world, it needs to look like it's really in the real world. So if something is sitting on this table in front of me, it actually needs to look like it's on this table or in my hand.
So that your eyes can focus on not just the object, but everything else that's surrounding it at the same time.
That's right. And so if you want to have a virtual object in the real world that looks realistic, it needs to match all the properties of light that are around it, right? If it doesn't match, then you have a lot of problems. Things don't look realistic, and it can really start to make you feel sick, right? You know, with this versus accommodation mismatch, you're going to get headaches and eye strain, potentially even nausea. In the mixed reality space, it becomes a really difficult problem to solve because the real world is always there, and it's completely unforgiving. It is what it is. It's always this ground truth reference point. So if I'm going to bring in a virtual object, it needs to look correct at all times. Displays today aren't really doing that. You know, there aren't really any light field solutions out in the market yet. And so while we've seen some pretty interesting AR products out there, the fact that they're fixed focus and they don't have light field yet and they don't solve this accommodation problem yet really limits the type of experiences that we can have, right? So we've seen a lot of these products out there. A lot of these are pretty cool, but you also notice that the experiences are limited to generally things that are a little farther away, you know, generally 1 meter or 1.5 meters and beyond, right?
And that's because their display technology, the way they're bouncing whatever display off of a mirror or projecting onto the transparent visor, that's just the distance. That's locked in.
Like most of the accommodation changes come within a meter. Is that like there's a lot of changes in your eye at that depth? Is that why?
Exactly. It's kind of this like the way you measure focus in diopters, right? Diameter diopters of focus you have, and it's 1 over distance. So if I'm at 1 meter, then that's 1 diopter. If I'm at infinity, that's 0 diopters. So you can see from like 1 meter to infinity, there's only 1 diopter change. But if I go from 1 meter to here, it's like 10 diopters of change. So you can see like how sensitive your eyes are to focus in this near range. And that's part of the problem on why this stuff is so important is you need to get things very accurate. And there's a lot of focus change, diopter change that's happening within a meter.
That's funny because in VR and AR, it's like that distance is where it becomes really interesting.
Near field activity on your desk, in front of you, interactions. So without light field, without light field display, AR would work fine if everything was projected into the horizon, into near infinity.
Right.
But if those images are dynamic.
That's exactly right. And we think that people think about the mixed reality space and think about all these amazing experiences, right? I mean, people are kind of have these amazing imaginations about what they want to have in these experiences. And the truth is, without a light field display, you're actually pretty limited on what you can show. That's why we think that light field is a critical part of the success of this industry going forward. And I think that if you want to build successful products and have really great, compelling experiences, no matter what they are, light field is kind of a critical component and critical part of that.
Well, let's talk about implementation then, because we tried the prototype, we tried the demo, and it was compelling. We could see, for example, an object close and an object far away beyond our arm's reach, and naturally shift between here and that.
Even with one eye closed.
Even with one eye closed, right? That's not convergence.
Right.
So how is that happening? I assume the system knows, the rendering engine knows what that distance is. It's just a Unity engine.
Right.
That information is being passed through. How is that image then running through your optical system?
So what we've seen is that people have been trying to solve this light field display problem for a long time now, for many years. And you see some pretty interesting research coming out of academia these days. When you look at those approaches, we didn't find an approach that really kind of checked all the boxes, right? You're looking for something that is going to be, not super expensive, pretty low cost. You need something that's very high quality, and something that you can bring to market. Actually talk about things like supply chain, quality control, and manufacturability. I mean, those are some serious issues, and on how to get technologies from research phase actually into products, like we've done in the past. And so because of that, we had to create a new approach. We invented a new approach to creating Lightfield that doesn't require very high computational power. It doesn't require any mechanical moving parts. So in the end, we actually have come up with this pretty neat solution that actually can create this Lightfield display that you guys experienced. And what's really nice about it is what we're doing effectively is we're creating this fixed point volumetric display. It's a volumetric display fixed to the eye boxes in front of your eyes. And because of that, it's generating essentially all the different focal planes that your eyes can naturally focus at.
But there's infinite focal planes.
All at the same time, correct. There's an infinite number of focal planes, but it's a digitized light field, right? So instead of light field is an analog signal, but if I can digitize it enough to a point where your eyes feel like it's continuous, then that's a good approximation of what that should be.
So are you rendering a discrete number of layers?
Yes. So we are rendering a discrete number of layers, but we're doing to you, it's all simultaneous.
Right.
And you'll see in the demo that there's a lot of points in the demo where you have continuous objects that you can get up close to, and it's like continuous from here to here, and you can focus at different points. There's even points where you might have dozens of objects kind of in your field, from very close, like inches away, all the way out to effectively infinity. You notice your eyes can just very naturally pick and choose which focus to look at.
Is the number of layers, is that gated by the projection system and the resolution of that projection system?
There's always trade-offs in the system, and I think that this stuff is always under development. But I think what's important is not really necessarily the exact implementation of it. But what's important is, can you get to a good enough experience, a compelling experience for the user in a way that's practical to actually ship into products, right? One of the things that's pretty interesting that I think you kind of brought up around using the one eye thing is because we're generating this volumetric display, we don't need to have eye tracking, right? And it's pretty interesting to have that experience where even if you close one eye, you can naturally pick and choose and adjust your focus between these different points.
The fear with eye tracking is it introduces this latency.
Yeah, I think eye tracking is an important part of these type of systems. It's not necessary to generate a light field display, but there are other benefits to Lightfield. People are already exploring that stuff in the VR space. So we look at things like foveated rendering. It's always good to reduce computational loads.
Definitely, but if you're going to tie it to the accommodation, you need really tight latency on that.
It could be potentially, right?
Yeah.
Yeah, and it also seems like the volumetric display area is tied to the eyebox. How much, in layman's terms, the field of view you get, how much you can move your eye around. Is that right?
That's kind of independent of the light field thing. Any kind of near eye displays generally will have a certain defined eyebox, right? So any display will have a certain kind of eyebox. Basically, it's the area that your pupils can move around and still capture all the rays the light rays are coming out of the display. When you start having a really small eyebox, when you look too far, what you don't want is to start losing parts of the image when you're looking at a certain part of the image, right? Other parts of the image.
Just back to this multiple layers thing for a minute.
Yeah.
I don't understand how there is an interference between the different layers. I mean, how am I not seeing two at the same time ghosting over one another or something like that?
You're seeing all of them at the same time, right? It's just like, think about in the real world, you are actually getting multiple focal depths from images all the time. So when you're looking at me, for example, you're focused on me, I'm totally clear,
right.
But you're also getting light from behind me, right? A bunch of different light from behind me at all different focal distances.
Right, but they're all coming from different distance or different positions.
Yeah.
With your projector, how is that coming from different positions as well, but just on a smaller scale?
It is coming. Yeah, we are recreating this volume of light coming in from all these different angles, but now these are optimized for head-mounted display, so they're optimized for the position of your eye. Right. It's just like if you're looking at me right now, and if you don't move your eyes, you can still see stuff behind you, and you can still focus back there too, right?
Right.
And is that volumetric display system
something
that's tied to the retinal display system?
Actually, it's not. So it's pretty interesting because this light field optic is it's independent from what we're doing from the retinal imaging side. But right now we look at the micromirror approach as being probably the best approach today, as far as resolution, fill factors, latency, and brightness. There's a really significant advantages to what we're doing right now, and we're tying these two things together right now because we think it's ultimately the best solution now.
You're running rendered imagery off of a Unity engine through a filter. There's some computation that's happening there. How computationally intensive is it to display for Lightfield?
It's actually pretty low. So the way that we do it is pretty interesting. the computational loads that we're doing are actually low enough that we have stuff running on mobile chipsets too. So today the demo you're seeing is running on, I would call it a VR PC, right? So like a Windows PC running Unity with a nice GPU in it. But we also have it running on things like NVIDIA Tegra or Snapdragon, right? So it's pretty interesting to see that the approach that we're taking for Lightfield can also run on mobile chipsets, which kind of opens up a lot of applications.
Each new layer that you introduced, it doesn't double your computation.
It's not quite that straightforward.
That's interesting.
Yeah.
And then the area of coverage, the field of view right now, I mean, you're in the prototype stage, but is the goal for the version of AR and Lightfield AR that you guys are targeting, is it full coverage for field of view, or as wide as possible? Is that what you're interested in?
I mean, I think ultimately, the industry knows where it wants to go. Like, we want to get down to something that's very thin and light, like a pair of glasses with a huge field of view, and that's going to take a little bit of time for the industry to get to. And step by step, I think people are going to solve these problems. Right now, we're very focused on solving the light field problem, which is, I think, a really big step to making a good experience. What I'd say about things like field of view is, for us, it's something that we understand pretty well, and there's a lot of adjustability in the system, right? And you asked a little bit before about things like, have you looked at different kinds of chips and different resolutions and stuff? And these are certainly all pretty simple possibilities that we look at. And there are other trade-offs too, the size and weight of devices, cost of devices. I mean, you can easily go to larger fields of view if you're willing to trade off some other things.
But those are all manageable costs.
Absolutely.
That will get better over time.
Yeah.
The approach you're going isn't going to be limited.
That's right.
In the end, so it could potentially happen.
Yeah.
With the looking at the prototype, like looking up close to how you guys are setting up the mirrors, it looks like you guys have the lights from your retinal display coming down. Opacity and how much you want to see of the real world versus the projected world and the AR world. That's a trade-off as well. The demo we saw was in a indoorly lit controlled environment. What are the limitations right now, and where do you see improvement?
Sure. Well, I would say, first of all, these are still prototypes. So we're kind of giving you guys a little bit of an early look on where things are. And with prototypes, there always are prototype issues. So you probably have noticed a little bit of artifacts here and there. Some of the things that we're definitely planning on improving are things like the transparency. It's definitely not as transparent as we want it to be.
When you say transparency, you mean so I can see the real world, not the transparency of the augmented objects.
Exactly.
Okay.
Right. The objects actually seem pretty solid, right?
Yeah.
It's some of these bright objects you absolutely can't see through them, which is pretty nice. But actually being able to see the real world a little bit better than what we have now. So obviously there's a lot of improvements that are in the works right now. It's not something we're really worried about. But one of the nice things I think about why we like using the retinal imaging technology we're using is because as a reflective display, it's really easy to couple in a lot of light, right? So the system right now is actually really low power. And by using a reflective display, if you wanted to go down applications of saying, like, let's say outside where it's really nice and sunny, then we can absolutely put in a lot more light for stuff like that. So it's pretty interesting to see a lot of the core advantages to using the retinal imaging technology, not only in the resolution advantages, but also in brightness and speed.
Yeah, one of the appeals of your first product, Glyph, was that as a display technology, it was different than a VR headset or looking at your phone. Yeah. But the inputs were all universal. You could plug it into a phone. You could plug it into a quadcopter. For this, because you have to run through some computation, are you focused toward AR as we see tethered to a computer, or is this a technology that you see can go be used elsewhere?
We think that AR really is going to be the future of these type of devices, right? And I think the AR world is not necessarily going to be a plug-and-play thing. Because when you look at things like Lightfield, when you put a Lightfield in it basically automatically requires that you need Lightfield input into it, right? One of the nice things that we've been able to leverage, though, is some of these platforms that are out there that people use, such as Unity. Unity becomes kind of like a unifying platform. And there are a couple of big platforms like Unity and Unreal and a couple others. Basically is like what all these different hooks and developers are all tying into. So it becomes a really nice platform to start out with and saying, hey, if you can develop on Unity, which is cross-platform, right, on mobile and PC levels, if you can develop on Unity, if you can create content on Unity, then with our rendering plugins, all the light fields just going to be rendered in the background. Right?
What does a light field signal look like? I mean, on a technical level, if I were to plug it into a TV and see your HDMI signal, is it a video signal plus metadata, or is it extra visual data?
There's a lot of different ways to encode that information. I don't know what it looked like actually plugged into a TV.
You know what I mean though? Is it extra visual data? Is it like a 3D signal where you've got extra video data? Or is it just extra metadata?
It's not extra video data. The extra data that's being sent is not a visual data. The extra data that's being sent is depth information about the images, right?
And so you're doing decode on the headsets themselves.
That's right.
Before it goes into the projectors.
Okay. Yeah, that's exactly right.
That's
so
interesting.
when you think about it, like an engine like Unity, for example, it's generating the entire 3D scene, right? So it knows where everything is.
Right.
It knows the depth of every single pixel in that scene, but when it outputs to a standard display, it's not outputting any depth. It's like taking a camera viewpoint and then sending out the 2D image of that viewpoint, right? So what we're doing now is, of course, we take that viewpoint, but we also ask for all the depth information of all the images in there that's also sent over to you. Now the headset can decode that and then turn that into that volumetric image that you see.
That's what the dream is for Lightfield cameras, right? They take that depth data as well as the image.
Yeah, so if you're familiar with Lightfield cameras, we're basically doing what a Lightfield camera is doing, but in opposite.
Right. You're doing it using 3D rendering.
Right.
Yeah.
And I think 3D, it's interesting because Lightfield capture is going to become more and more prevalent, right? So you see companies like Lytro and Otoys doing some rendering stuff. So it's pretty interesting to see, like, as the captured Lightfield content starts becoming more available, it's going to be interesting to see, like, what that stuff looks like in Lightfield displays. Because I think these are very harmonious kind of applications.
But it's definitely not a requirement for getting the benefits.
No, absolutely not. And like what you saw today is almost all existing Unity content from a lot of existing VR experiences, a lot of content from the standard Unity store. Because Unity already knows all this information about this content, we're just asking it to output it to us, and then we can render it correctly on our side.
Yeah, I mean, you could work on this technology forever until it's perfect. I mean, until costs come down, you've iterated, iterated. You're clearly at a point of the prototype where you're ready to show people in public. So is this, how close, I guess, is this to something that you feel can be in a product?
It's close. I would say sit tight. We'll make some announcements later this year. But we're really excited because, I think people are starting to hear about why Lightfield displays are so important. There's been a lot of interesting hype around that. But we just want to show people. Like, I think very few people have ever seen that experience, and they conceptually can understand it, but it's very different when you actually put it on, look at it, and experience it. And that's kind of what we're out to set out, is saying Lightfield technology is great. We think it's required for a good AR experience and good mixed reality experience. And we want to start showing people and say, hey, this is what it is, and start spreading the word, right?
What markets do you think AR is right for in the near term of like 2017, 2018?
In the near term, I mean, the enterprise market is already desperate for this stuff. I mean, you're already seeing enterprise adopt things like HoloLens all over the place, right? In like industrial applications, engineering, and medical. I mean, that's just going to take off, right? It's interesting, I think, is to think about what's going to happen in the consumer space, right? Because in the consumer space, I think the challenge is what are the key use cases that people are really going to see a lot of value out of, right? What am I going to do with these glasses that I put on that is going to be much better, and I'm willing to put something on my face rather than using my phone or my tablet, right?
And how do you get the cost to a level where the consumers can justify it?
Right, yeah, exactly. And it becomes a really kind of a balancing act between cost, quality, size of the device, form factor, and application, right?
And application versatility, so it's not just locked to whatever platform you or one person is developing. It can already be adapted to existing content.
Yeah, I mean, if you look at even the glasses you're wearing right now, right? I would bet that if you didn't have to wear them, you wouldn't be wearing them, right? They're still kind of a pain in the butt to like put on all the time.
No, that's debatable.
Yeah,
It's kind of an image thing.
all right. That's image aside.
But you would agree that the consumer product is further off than the next 2 years?
I think that the industry, where the industry at today is enterprise is using it right now,
right?
And the consumer market doesn't exist yet, right? So it'll take a little bit of time, I think, for these markets to mature.
Yeah. Awesome. Well, thank you very much for the demo today.
Thanks.
Okay, Jeremy, what did you think?
All right, so this is something new,
Yeah.
and I got to give them complete credit for this. Being able to focus on something that is clearly augmented reality, but with one eye closed, is something that I've never experienced before, and I've been waiting for this. Like, I've been waiting for this since virtual reality, and certainly with the other augmented reality displays. I think that solving this, what did they call it? The Vergence accommodation.
Yeah.
Vergence accommodation problem.
Yeah.
is very, very important in order to create a very natural experience, in order to reduce headaches. I mean, I think people are susceptible to this kind of dissonance without even realizing it.
Right. So it actually applies to both VR and AR.
Absolutely.
And in VR, not having a light field display, you can get away with that because there's nothing to compare it to. You're always focusing the image to infinity based on the lens. And things still look like 3D, and you still get a sense of depth because your brain has been your lizard brain works with the convergence cue,
right? And
stereoscopic imaging.
But it's experiencing 3D in the same way that we've been experiencing it since the 1950s with the anaglyph glasses. Right. It's just convergence. It's making your eyes do this when things get closer, and this when things get further away.
Yeah, which for some people creates eye strain. It's not as comfortable.
Right.
And the way your brain actually wants to sense depth is a combination of many cues, convergence being one of them, accommodation being the other one.
Which is the way that your actual eye lens actually refracts.
Mm-hmm. Yeah, it's just a simple thing. If you hold your hand up to your face and you change your focus with one eye, change your focus from the background to the foreground, to the background, to the foreground. That's accommodation.
And that's what camera lenses can do. Like, that's how they create depth of field, cinematographers forever have been controlling what you're focusing on. And you've never been able to, up until now, you've always had to control what people focus on in VR and AR. But with this technology, it's much more natural. It allows the user, the person wearing the device, to focus on whatever they want to.
It's not just more natural, it's almost more essential. I mean, the two AR displays that we've tried recently, Meta being the most recent one, and Avegant, one is a light field display and one isn't. And Meta, while the tracking I think it's better and they can do more and they created a bunch of software for it, it didn't solve the light field problem because the objects you would still be focusing on them with convergence. You would have a very clear, floating brain in front of you, and when you got closer to it, it would still be sharp, but everything else wouldn't necessarily match the focus of it.
And I noticed with their demos, they didn't augment the actual space. Not that it wasn't capable of it, but I think that would have been a telltale sign of lacking that volumetric display.
In the near field.
Exactly, because with this demo, if something is in your hand, it's in the same focus as everything else as your hand. Right, and that's the magic. Because I reached into this aquarium that was augmented onto a table, and it's the most holographic thing that I think I've ever experienced when it comes to AR. Because the turtle or fish or whatever it was, the projection actually was at the same focal depth as my hand, and that was just like, yes, that's what I've been looking for.
And it was dynamic. As it moved and your hand moved along with it, it would stay on the same focal plane. And as your head moved toward it and your eyes were naturally adjusting to your hand and the projection, they would still be aligned.
Right.
And that felt like something magical and essential.
Yeah. Now, just to throw out a quick caveat, this is all sounding great and magical, but it is a very narrow field of view. This is something that coming from VR is difficult because we've been spoiled by 110-degree field of views, and what's not in your field of view is cut off. Right. In VR, you only get the virtual field of view.
With AR,
they encourage you to have the world behind you. And then what's projected is a much smaller portion of your field of view.
And in this case, that field of view, that box you see in front of you, it's larger than a postage stamp. That box actually is a shade darker than the world around you. You're looking through this visor, but you see almost like a one step down, a tinted view of the world, which is something they said they would be working on improving.
Right.
But it helped to make the objects brighter.
Yeah, and it also depends on how bright your environment is and things like that. But frankly, I think they made the right choice with this because I would prefer a more opaque augmented image, which the darker real world actually creates.
Yeah, the thing that worries me is that I don't know if this is a product. Unlike their first product, the Glyph, which was like a display, you can plug a phone into it, you can plug a game console into it, and you get a stereoscopic 3D
portable TV
image, portable TV. Here, because they're not making tracking devices, they're not making software, they're not making a headset even, they're just working on the optics.
Yeah.
I'm a little skeptical when they say that this will be something that's going to be in people's houses in a year or two.
Well, they're not. I mean, my impression was they're not even thinking about people's houses yet. Like, their priority is going to be enterprise. They want companies to buy this that they can design in and demonstrate what their products look like to other people. People for whom cost points aren't as important and they can charge a higher price. But also, Yeah, I mean, they're not developing any of that tech. They're relying on third parties to develop the tracking systems. My impression is they actually want to be a display manufacturer, that their volumetric technology is where their focus is, and they would love to supply those to other vendors, maybe not unlike Valve developed VR and passed it over to HTC.
Right, and the other thing I'm trying to wrap my head around that we've been talking about since we got that demo is how does this volumetric display work? I still can't figure it out.
Well, now they told us that the HDMI signal, like the video signal, was one two-dimensional image.
Right. If you think of this, there are discrete layers, right? You're going to be focusing on the asteroids in front of you, or it moves further away. It's maybe some number of discrete layers of focus that works in their system. They wouldn't tell us how many, but they also said that it wasn't sending that many layers of signals from your computer.
It's one layer of signal from the computer.
Which, with depth data.
But with the depth data. So their HDMI signal wouldn't even be visible on a TV because they're actually sneaking information into this HDMI signal that it still makes it compatible with your video card, and other HDMI receptacles, but they snuck it in there, and they use that metadata to extrapolate depth data.
But how does then that get projected onto something that fits in this headset, especially when they're using the same type of the Texas Instrument retinal displays, projectors, the DLP displays as the Glyph. Now, he also said that it wasn't dependent on those as well, that this could be done, but that's just the technology they've been set up with. And the other thing that kind of blew my mind is that this is supposedly not very expensive optical hardware. It is custom, but it's not something completely designed and manufactured from the ground up. They said they were confident about that price point. So for me, it's, how does this Lightfield display work? What is the snake oil part of it? Because it definitely did work, at least in the demo that we saw.
The conversion happens in the headset. That's my understanding. Because if it's getting this HDMI signal with this metadata, that gets transferred into something volumetric in the headset. That they have some sort of smart device in there that does this refraction, that creates this light field image. And I asked him, I said, so is my eye receiving just what's in focus? And then at first I thought they must be using eye tracking or something, but no, there's no eye tracking at all. It's instantaneous. So if you look at something else in the image, your eyes will change focus and that will come into focus. And they said that my eye is actually receiving multiple depths of information
all at the same time.
In the same way that the real world projects multiple depths into my eyes.
And scaled down.
Right.
Scaled down to something that still fits in their headset, and then through a lens, that gets extrapolated to one diopter, half a diopter, away from you. Most importantly, in that near field.
Yeah, that was interesting. He said that to a meter apart, everything past a meter is relatively the same focal depth.
Yeah.
But everything close to you, that's when your eye, the convergent part of that focus that we're talking about, and convergence. Accommodation. Both of those have to do a lot more work in order to focus on the image.
Yeah, and we tried to stress test that demo. When we were sitting with the virtual solar system in front of us, I would just stand there with an asteroid in front of me, focusing on the asteroid, on the sun, on the asteroid.
Because that's the new part.
On the sun. Yeah. Not moving my head, not moving my eyes, just refocusing. And I was able to do it.
I'm sure once these displays come out, some of you will take them apart and figure out how they're doing it. But we have thought about how they're doing this and how many layers they must be interpreting. And it's just beyond me. It's a really, really fascinating technology.
Yeah, it's one of those things where we feel like after getting this first taste of light field imaging, we don't want to go back. It's not ready for a product yet, but this feels really exciting the same way using 90 hertz tracking and displays for VR was a couple of years ago. And we can't wait to see what comes next. We'd love to hear your thoughts on this, how they could possibly do it. Post your comments below. Subscribe to our channel, like this video, and Jeremy and I will see you next time.